Streaming enabled. Back to there. Should be ready in 10 seconds. Streaming enabled. Back to there. Should be ready in 10. All right. Let's go. All right. So thank you for joining me today. The topic that they asked me to present is one we've done for you guys in person in the past. We're doing it online now, hoping that we can capture some of you guys that aren't able to physically make it in here sometimes. So we're going to do VAV systems, variable air volume. We'll go through how these systems work, how they've worked historically, what you might have to do nowadays in the modern era of codes for the past 10 years to make them continue to work correctly and legally. And we'll answer any questions. And by we, I mean me, because no one else is here today, because everybody else left and ditched me. My information, my email is down at the bottom. If you want to hunt me down later and ask something specific, that's totally cool. No objections to that whatsoever. So the primary reason to have a VAV system historically has been to have individual control in individual rooms. So for example, in an office building, each person would love to have their own thermostat, but I'm not buying everybody their own air handler because that would be ridiculous. So a VAV system allows us to do that kind of thing. So no one's getting their own air handler. Already mentioned that. So instead, what we're going to do is we're going to have a single air handler, or it could be several of them, right? Depending on how big the building is. A single air handler mounted in the building or on the roof, package rooftop unit, that's VAV style. We'll talk about what that means in a minute. Providing cold air down the duct. And then each individual zone will have its own branch coming off the duct like you would normally have, but there'll be a damper inside there. So there's a VAV terminal. I'll show you some pictures of it later with a damper in there that lets more or less cold air into the system. So that's a VAV system. You got an air handler providing cold air down the duct. And if this zone wants more cooling, its thermostat tells its damper open more. And if this zone wants less cooling, it tells its damper close down some. VAV systems, by definition, are cooling only systems. That is what they are. If you need to have heating in your system, VAV is probably not the right thing for you. There are ways to add some heat on a zone by zone basis, but what we cannot do, at least not do very well, is have this air handler be the heating source of the building. So VAV is correctly used in buildings that need cooling year-round all the time. If your building does not need year-round cooling, you probably should not do a VAV system. You might want to do a zoning system still, a dampered zoning system, and that's possible, but it wouldn't be VAV. So a VAV system provides 55-degree cold air all the way down this duct all the time, no matter what, all day long, and each zone just gets more or less cold air. It doesn't turn the heat on in the main air handler. There's some exceptions to that, which I'll point out, but that's the main deal with this. So large commercial buildings is where this normally would historically be. So reasons why people want VAV, they want individual control. Everybody wants their own thermostat, right? That's a benefit. Diversity is also a benefit. Maybe this project is 60 tons of cooling when I look at the loads of the building, but not every room needs the same amount of cooling at the same time, right? The north doesn't have any direct sunlight. The east gets it in the morning. The west gets it in the afternoon. The south gets it at midday. The interior core doesn't get any sun. So I don't really need all 60 tons at the exact same moment. But if I have a constant volume system, I'd have to get a 60-ton unit. Well, by having a VAV system, I am allowed to take diversity into equation, which for rough discussion means that my air handler should be about 80% as big as it would be on a non-VAV system. So instead of 60 tons, I should have picked easier math. Instead of 60 tons, it would in fact be a 48-ton system. It's not always exactly 20% smaller. It just depends on the way the loads are, but you can look at the individual loads and what time of day and year they peak. And usually a good software package like Carrier HAP or Train Trace or something like that can help you decide when those loads peak. And you can put a smaller air handler in. It's done for energy savings, specifically on the fan side of the equation, primarily. There's other savings too, but the fan is the big one. You have a VFD, typically VFD-driven fan, that helps you save quite a bit of energy on the fan usage. It is pretty flexible. It is not impossible. In fact, it's fairly common to design an air loop that goes around one floor of a building without knowing what the tenants are going to be on that floor yet. And then as the tenants move in, the ducts can be tapped off of that loop to provide air in certain quantities to certain areas depending on what's going on in that particular zone. So it is pretty easy to expand and adapt that system by tapping new zones in off the ductwork. And you have the ability to stage things down. Like if some of the people in the office leave at 4 o'clock, you can put their thermostats in setback, but other people are there till 6:30 p.m. Those stats can continue to be in occupied mode, and you can take advantage of not fully heating and fully cooling every area at the same time. There are disadvantages to these systems, specifically in this case, if you have zones that need heat. When you have zones that need heat, you got to come up with another way to heat those spaces, and we'll talk about that in extensive detail today. VAV equipment is also fairly expensive because of some of the things that I'm going to require you to have here in a minute. It does become more expensive than constant volume equipment, but it saves more energy, so there's a trade-off there. So the kind of components that we have in a VAV system, this example obviously is visually a rooftop unit, but it could just as easily be an air handler inside a mechanical room. So I have a piece of equipment that's going to be my primary cooling source, my rooftop in this particular case. That is going to provide 55-degree air down the duct system all the time, all day long. If I need heat, each individual zone will have its own duct heater. Duct heater meaning electric resistance heat or hot water coil, or they could have a baseboard heater or even an old school radiator if they really want to. Something else providing heat in that zone. Typically, only the perimeter zones need to add heat. Let me see if I can find we'll use this here. Let me get the John Madden pen out. All right, let's say this is my building. Whoa, what the heck happened there? That was super weird. All right, that's gonna be my building either way. Oh, it's not gonna be my building. My building's gonna have this weird line on it. All right, my building has this weird peninsula on it. All right, say this is my building other than this weird thing going on over here. All right, the interior of a large I don't know why it's doing that, man. The interior of a large commercial building needs zero heating. It does not need any heat. If everybody around him is 72 degrees San Diego, the perimeter, in other words, and by the way, the perimeter could be physical walls, or if it's not, you can just estimate it being like 15 feet from the exterior wall or so. It'd be where my core starts and my perimeter ends. Once you get that far into the building, this wall being cold has nothing to do with what's happening in the middle here. So if all four sides of me are 72 degrees San Diego, and the floor above me 72 and the floor below me 72, the people in the middle, I don't know what's going on with that, man. I can't use that. Erase all ink. Let's do that. The people in the middle do not need any heating at all. It's cooling only all the time, year round. When it's negative 23 degrees, cooling. When it was polar vortex, negative 27 a few years ago, we had people calling to complain that their chiller wasn't running. Never been negative 27 in our lifetime around here, so we didn't think about it. But their chiller actually shut down, and they had no cooling in the middle of the building when they needed cooling, because year-round, you need cooling in the middle of a large commercial building. So this air handler is providing 55-degree air down the duct all the time. It's going into these individual dampers. They each have a thermostat saying, I'd like more or less cooling. And if that's a perimeter zone and it gets cooler, it can engage its local heater, duct heater, hydronic coil, baseboard, etc. I'll have diffusers coming off of all of those VAV boxes, probably more than one. That'll go to 2, 3, 4 diffusers serving that particular area of the building. I'll have all these diffusers on there. VAV diffusers are not the same as regular diffusers. They are special, or at least they should be. Sometimes people put cheap diffusers on VAV, which doesn't help us any. When this damper starts throttling back, I will have less airflow coming out the diffusers. If I have a low-end, entry-level, constant volume design diffuser and I throttle the air back, the diffuser loses its throw ability. I want the diffuser to throw the air out. I don't want it to just come straight down. If it comes straight down, it's probably going to go on my head, and now as the occupant, I'm going to be pissed off. If you get a VAV diffuser, a diffuser specifically designed for VAV, and Titus and Kruger and all these people have that thing, then in those cases, even on low turn down, the diffuser should still have good throw ability. There's actually a rating for that. It's called ADP. That's a whole nother hour-long discussion. But you should get a diffuser selected that's either labeled as a VAV diffuser, I'm not talking about VAV where they put a little damper in there. I don't want that. I want a regular diffuser that's designed for VAV systems and has a good ADP throw. So you need those diffusers on there. You need the return grills that are ducted, or in this case, open plenum to bring the air back. You need a thermostat for every single zone that's going to have a damper. You need a static pressure sensor in the duct system. There's going to be a VFD, or in the olden days, there could have been, inlet guide vanes or other stuff. But nowadays, it's always a VFD 100% of the time. A VFD ramping that fan up or down. As these individual zones start throttling their dampers closed because they want less cooling, pressure builds up in this duct system. That pressure sensor senses that and throttles the fan back. Essentially, it says, hey, if you guys don't want my air, that's fine. I'll just give you less air, and whoever wants it can take it, and everyone else, you can pound sand. Not my problem. And then as the zones open up to get more cooling needs, the pressure sensor recognizes that the pressure has dropped in the duct, and it then increases. If you guys have any questions as we're going, feel free to type them in that chat. I said it again. Type them in the question and answer box, and I will do my best to answer them. And if your question's really weird and complicated, then what I'll probably do is find a way to unmute you and let you interrogate me that way. Well, as stuff comes up, just type it in, and I'll do my best to answer it. All right, I'm going to keep moving on here. All right, there are some things that are going to be requirements of our air handler. So specifically, a VAV air handler has two very major things different compared to a constant volume air handler or rooftop. One, I already mentioned, is a VFD. I need to have a way to slow the fan down. Now, I can have a VFD on a regular quote-unquote constant volume system nowadays. Typically, that is called SAV, staged air volume, and it's a two-stage fan. It goes to one speed when I'm in cooling 1 and a higher speed when I'm in cooling 2. And that's all it does, right? 67% for stage 1, 100% for stage 2, that's it. We're using a VFD on staged air volume, constant volume as a two-speed motor, basically, because two-speed motors with double the windings actually cost more than a VFD does nowadays, so we use a VFD to do that. We are not talking about that. We're talking about a true VFD application where the VFD is going to ramp this thing up and down to maintain a specific static pressure. So more than two speeds. I'm going to have hundreds of speeds, each little incremental one in there. So I need to have that VFD in order to have a VAV air handler. I also need to have a boatload of cooling staging ability. So option 1 is chilled water with a modulating valve. Modulating chilled water valve gives me nearly infinite capacity control. It would be the best way to do it from a control and comfort standpoint. But not every building gets a chiller, right? So that's not always going to happen. So if you're going to do it with DX, direct expansion systems, you have to have lots of stages of compression. How much is lots? I'd like to have 8 stages of compression. If you can't get me that, 6 is really, really good. 4 is the bare minimum. If you can't get 4 stages of cooling, you should not put this in a VAV application. It will die. The VAV system, as you're going to find out, we're controlling it to maintain a specific discharge air temperature, 55 degrees. And if I don't have enough stages to do that, it ends up hunting and it bangs one compressor on, off, on, off, on, off, on, off, and just beats the hell out of that thing. So you definitely cannot use 2 or 3 stage machines to do VAV control. It's got to be bare minimum 4 stages of compression or larger. Now you could have one compressor and have it be variable capacity compressor, like inverter driven or digital scroll. That would be fine, but you can't have on-off compressors. You could have 2 compressors that are recips. That's not something we do anymore today, but you might have those out there. And if it's a recip and you have unloaders on it, you could definitely get enough staging capacity that way too. They have to be electric unloaders. Pressure unloaders do not work on VAV. Has to be electric unloaders if you got a recip. If you're so young that you don't know what a reciprocating compressor is, then that's okay. Oh, I could have did this. This is a better than my crappy drawing that I drew earlier. This is a better drawing of me saying, here's the interior zone, here's the perimeter zone. I need to divide this up into VAV zones. 9 zones is about the minimum that I'm going to have because I need to have one for the core because that guy's cooling all the time, no matter what. I need to have north be separate from the other directions because he never gets any sunlight. East gets sunlight, but not the same times as south and west, right? So east, south, west, and north all need their own. Interior needs their own. Now I'm up to 5. And then the corners, quite frankly, are messed up. The corners have windows on both sides. If you try to put them on either of the other two zones, it pisses people off. So they really need their own zones. Now you're up to 9. You may do more than 9. You may divide it further. Maybe this is a really, really big zone in the middle, right? And maybe the left half side is accounting and the right half side is IT support. And the IT people are there, till 10 p.m., but the accounting people go home at 5. You may want to have different zones because the schedules are different, right? Or maybe this zone over here, maybe it's actually 3 offices and then a conference room. Well, grouping the 3 offices together is okay. I mean, everyone wants their own thermostat, but everyone's not important enough to get their own thermostat. But putting the conference room on with an office is a disaster. That conference room might have 15 people in it, and all of a sudden it needs cooling while the office over there needs heating. So if there's a conference room, you always split it off on its own. If there's a classroom, you split it off on its own. Those spaces get used differently. So you need to divide the zones based on the cardinal direction that they're facing and how they're utilized, time of day, and occupancy variability. Now, this gives an example of a very small system. VAV is usually much bigger than this, but just to give you an idea, there's 1, 2, 3, 4, 5, 6, 7, 8 zones in this case. I know I just said, oh, you got to have at least 9 minimum. In this case, this zone over here on the top, on this side of the equation, is butted up against a manufacturing facility. So it's not really an exterior wall. So it's really just an extension of the core. So this area is basically the same thermal needs as this area is. Plus, this is the bathrooms over here. So that kind of takes that out of the equation. But they got one zone right here, a VAV zone with an electric heater, and that's servicing the west. The corner has its own zone with electric heater, or it could be hot water coil. The south zone, its own damper, electric heater. This corner, own damper, electric heater. This one, damper, electric heater. This one, it could have been shared with this guy, but this was a conference room. So conference room mixed with this private office, not a good mix. They each should get their own stat, and they all have electric heaters because they're on the perimeter. The 2 interior zones each got their own stat. They do not have that little black box on there, which is the electric heater, because I don't need electric heater on an interior zone. Everybody with me so far? If anything comes up, type it in, man. All right, I mentioned having a VFD on there for fan control, and that is the modern way to do it. I will briefly mention some of the older ways because you will see these in the field. They do come up once in a while, although I've been doing this class for, I don't know, 20, 25 years or whatever, and it's less and less and less of this occurring. So inlet guide vanes are the primary way that we control the airflow on a VAV system in the 60s, 70s, and even 80s. And then VFDs started getting really popular in the 90s as the cost came down and reliability increased. So this is the inlet to my fan, right? So the air would normally get sucked here in the eye of the fan. It goes around the swirl because it's a centrifugal style fan, and then it would eject out the side here and go down the duct. What the inlet guide vanes do is they have an actuator on them, and those little blades open and close more or less. So basically, you cut the airflow off that's being sucked into the fan in order to provide less airflow down the duct system. You could also put dampers like that on the discharge of the fan instead of on the inlet. Nobody does this. I don't think anybody was doing this. I mean, someone did it enough to make this drawing, but it was not very useful. It does not really save any energy, whereas the guide vanes kind of save some energy. So this is like not happening. No one's doing that. So it was guide vanes for the longest time. Then it was guide vanes and VFDs, and now it's all VFDs, right? The reason we use VFDs is VFDs save a bunch of energy compared to these other options. It varies the amount of power being sent over to the motor to begin with. If you didn't know, fan systems are pretty grossly oversized. So ramping them down is normal. If you ever see a VFD on a fan or a pump operating at 100%, I guarantee you that something is wrong with that VFD control. It should not be, or someone put it in manual and just cranked it to 100, right? It should never be at 100% because that means someone actually designed it perfectly and did not oversize the fan, which we know did not happen. So it should always be modulating something below 100%. To give you an example of why VFDs are significantly more popular than inlet guide vanes now, other than their reliability improving and the cost going down, is that they save a bunch of energy. This is showing an example fan that costs $1,000 a month to run, so it's a big-ass fan. Not a big-ass fan, the brand, but literally a big-ass fan. At 100% speed, it would cost them $1,000. When they slow it down to, on average, 75% speed, it only costs $400 to run. Most people would think it would cost 75. Oh, I reduced it 25%. Give me my 25% energy savings. But it doesn't have a linear relationship. It varies as the function of the cube. So the savings is actually pretty substantial. If you can ramp the fan down a little bit, you can save a bunch of energy. If I cut the fan speed in half, it's obviously not 500 bucks because it's got to be less than 420. It's only 125 bucks to run it at half speed for this example. So you definitely want to be able to ramp these fans down. Um, this is due to the fan laws, or if you're a pump manufacturer, you call it the pump laws. And if you are Switzerland trying to be nice to the fan and the pump guys, you call it the affinity laws. Plus, it sounds like superhero stuff, so it's pretty cool. VFDs also help out in terms of being a nice soft starter. They don't bang on. You don't hear ductwork expanding. You don't hear belts squealing. They ramp up slowly. So it does have less wear and tear on the motor and belts themselves. And you avoid demand charges if your building is having issues with that. Paybacks in general on VFDs are actually pretty good. VFD costs have gone down and electric prices have gone up over the years. So paying back a VFD is pretty attractive upgrade if somebody wants to abandon their inlet guide vanes on their old air handler, if they still even have that thing, and upgrade it to a VFD. This is why a VFD will save you money, if you will. So on the bottom axis here, we have the speed, RPM. On the vertical axis, we have the flow, CFM, as well as the brake horsepower. So this orange line is the flow. So let's say I start over here at 2000 RPM or whatever this was supposed to represent, and I drop it down to 0 RPM. Obviously, my horsepower goes down to nothing as well because the system is off. But if I start at 2000 and I go down to 1000 right here, my RPM got cut in half. My airflow got cut in half. But look what happens to the brake horsepower. It goes down on a very sharp angle like that. That's because the brake horsepower varies out as a cubic function, if you guys are good with math, compared to the horsepower. So every little tiny bit reduction in RPM is a pretty substantial reduction in the brake horsepower. This just was an example of what I just said. We cut the speed down. In this particular example, we cut it from 1000 RPM down to 677 RPM, and that resulted in a 69% reduction. So the speed went down a third, but the energy went down more than 2/3. So that's why I want to ramp these things down. When someone doesn't want the airflow and their zone throttles back, let's just stop making that much airflow. From an energy cost standpoint, brake horsepower, compared to the CFM, this kind of gives you a representation of what's happening with these various technologies. So this orange line, the dotted orange line, that was the inlet guide vanes that we've had for decades and decades. As you throttle back those vanes, it did in fact reduce the energy usage of the motor. The motor would ride the curve back along with those guide vanes versus just straight riding the curve. You can straight ride the curve, which means you don't put anything in. You just let the zone damper shut and dude, whatever happens, happens, man. Like, it's fine. I don't care. Right. And that fan will draw less amperage as it ramps. As the airflow gets restricted, the fan will move less air, draw less amperage. Still move the same RPM though. So it does reduce down. The discharge dampers were actually slightly worse than the riding the curve. So no one did discharge dampers. So riding the curve was the poor, lazy man way to do it. Sometimes even caused the motor to overheat. And the guide vanes was the good upgrade to that. And then now here we are with the red line with the VFD. So the VFD is by far the way to go. It's a much smoother line. It's lower than the other line. The only point in time that the VFD would cost more to operate than doing nothing would be if you're at 100%. At 100%, meaning you don't slow the fan down any way whatsoever. In other words, you don't even need the VFD. Then in fact, doing nothing would be better than buying the VFD because the VFD has some waste heat associated with it. All right, questions. I know I'm talking fast because I have a 3-hour material to do in an hour 45. And I don't like to cut things out, so I just talk faster. What kind of questions you guys got? Oh, good. Questions about my hairstyle. Thank you. No, no one asked that because no one cares. All right. Well, unless you have questions, I'm going to go ahead and keep talking here. So that's on the fan side. I mentioned you need to have VFD fan control based on a pressure sensor in the duct in order to have a VAV system with zone dampers on it. The other thing I said you needed to do, different than a constant volume unit, is you need to have capacity control of the compressor. You need to have modulating chill water valves, you need to have an inverter-driven compressor, or you need to have multiple stages of fixed-speed compressors. The way that I like to describe that is that you don't want to use more compression than you need. So, for example, if you are cooking and you're making a bunch of stuff, I could have 5 burners on with all 5 of these pots. Like, let's go, man. Let's crank it all up. But obviously, I turn off the burners I don't use. But if I'm not doing that and I'm just at home and I'm making a pot of pasta for just myself, I don't put all the burners on and then set one pot in the corner. That's ridiculous. I just put one burner on for the one pot. You only need as many burners on as the amount you need to use. So the same thing's going to happen with the cooling control. I don't need 100% compressor if it's not a day where I need 100% compressor. I need a way to ramp it down. So that's what we're going to talk about, ramping that down. And we'll talk about the different technologies to ramp it down. So this is just a visual for you of how much time we spend heating and cooling in the Chicagoland area. This is bin hours. So if you didn't know, there's 8,760 hours in the year, and this graph represents all 8,000 plus of those hours at the same time in little 5-degree bands. So, here's 80 to 85, here's 85 to 90, here's 90 to 95, and this is how many hours you have. So hours that are 95 degrees of the whole entire year, we have like, I don't know, what do you want to call that? 30, we'll say 30 hours a year, we're above 90 degrees on average on a rolling 30-year basis, right? And then times that we're at -5 to -10 is probably like another 20, 30 hours over here. And everything else is going to be in the middle. For example, we spend a lot of time right here between 60 and 65 degrees outside. Today, in other words, today. We spend a lot of time from 35 to 40 degrees, right? And this tells you the months if you care what months these things are happening, right? So what I want to do is I want to have a system that can do this. I can cool your building on a 92-degree day, but when it's not 92 degrees, I want it to be kick-ass on all these days too. Because if it's really good on a 90-degree day and I have no way of ramping it down, it's going to suck pretty bad on all these other days. So I want to be able to control that part load for VAV or other systems, by the way, but VAV especially, because I'm not only going to have days where the weather says I don't need as much cooling, I'm going to have zones that are barely in use, and the zones don't need as much cooling either, and they shut their dampers down. So I really have to be able to ramp down for these days. So ways that I can control the cooling capacity. I could have a single on-off fixed speed compressor, just like you have probably at your house. The compressor turns on, the compressor turns off, and I turn it on or off more to get more or less cooling. I will get the desired effect. I will get the amount of BTUs of cooling that I want, but I'm gonna have to run it 10 minutes and then leave it off for 3 and then on for 9 and then on for 4 and whatever. It's gonna cycle on and off, which means that I'm not gonna have the coil wet all the time. That's a problem. I want the coil to be cold all the time. I want it to be below the dew point all the time because it's at cold at the dew point. It does a really, really awesome job at dehumidifying. Believe it or not, it also saves a bunch of energy. If you can get the humidity right in a building, you don't need it to be as cold in the building. So instead of cooling it down to 72, you can cool it down to 73 or something of that nature. Or it can be real extreme. My house, I cool it down to 77 to 78 degrees in the summer. 77 degrees is my set point in the summer usually. That sounds really high for most of you, but I do all kinds of weird crap in my house to dehumidify the hell out of the air. So it's like 32% humidity. So 77 feels cool. It's like really nice, right? Whereas if I had 60% humidity like you, then I have to drop my stat down to 69 or 70 degrees for it to feel okay. So you can use multiple compressors to do that. You can have 2 circuits. Each one can have its own compressor. Now I got 2 stages. 2 stages is not enough for VFD, or excuse me, for VAV, but it does help me out on a constant volume system getting better control. You could also do what I'm showing in the picture here, which is have 2 compressors doing 3 stages. That sounds a little bit weird, but just imagine for right now that this first compressor is a 4-ton compressor and the second one is 6 tons. If I run them both, I have a 10-ton air handler. If I run just the little one, I have 4. If I run just the big one, I have 6. So I have 4, 6, and 10-ton capacity in that case. So if you unequally size, I don't know if that's even a word, if you unequally size the 2 compressors, then you can get 3 stages out of 2 compressors. And that's, in fact, what's being done in this situation here. But once again, 3 stages is not enough for VFD. If you have reciprocating compressors, anybody deal with recip still? If you do, just type something in the box so I know if I am 15 years beyond what you guys are doing or not, or 15 years behind, I guess. See if this makes any weird lines when I try to draw again. Oh, it does. I don't know why it does that. That's super freaky. There's no way to turn it off. It just is what it is. All right. So if you don't know how a reciprocating compressor works, my crude drawing might help us. All right. Let's say that this one is one that has you know, 6 cylinders to it. Think of it like a V6 engine, right? When this piston goes down, that piston goes up. They work like yin yang buddies to each other. But I don't need all of them. I can put them in groupings, in pairs. That line's killing me. So that's 1, that's 2, that's 3. I can group them together. So I can basically put an unloader on these and an unloader on those. So if I don't turn the unloader on, I have all of the capacity available to me. If I turn unloader number 1 on, then I have 2/3 of that compressor available to me. And if I turn unloader number 2 on, then I have only 1/3 of it operating. So I can put 2 recip compressors in the machine, and I can put unloaders on 2 of these on 1 of the compressors. So with that, I can have, and the other compressor doesn't need any unloaders. It can just sit there doing its own thing. Why is that doing that? Not that this drawing is good in any way. It's a shitty drawing. I get it, right? So if I can run, let me go back to the laser. I can't handle that anymore. I can have just this bank on for 1/6 of the capacity. I can have this and this for 2/6. I can have all of these on for 3/6. If I want 4/6, I turn these off, have these guys all on, plus him, that's 4/6. These guys plus those 2 is 5/6, and then everybody can also be on for 6/6. So I can put on loaders on just 2 of the possible 6 pairs, and I can use intelligence in my control system to get all of the unloading I want and get 6 stages out of 2 compressors that way. If you are going to retrofit reciprocating compressors into a VAV system to make it VAV where it used to be constant volume, 1, you should evaluate your life and decide if a recip compressor should continue to be reused at this point because it's probably 25 years old. But 2, you have to get electric unloaders. You cannot do VAV with pressure unloaders. Pressure unloaders wait for the refrigerant pressure to change, then they take banks of the compressor offline. That won't work on VAV because for VAV, we're going to have a sensor in the duct controlling temperature in the duct, in the supply duct, and it changes super quick. So the pressure unloaders aren't quick enough to be used on VAV. If you want to use unloaders on constant volume air handlers with reciprocating compressors, you can use pressure unloaders. That's the preferred method. But if you have VAV, you have to go to electric unloaders, and you have to use an electronic controller to stage them up and down. Hopefully that makes sense. Other things we could do for capacity control, assuming that you're not going to do chilled water, because chilled water, it's a 1-second discussion. We're done. Chilled water modulates, we're good, right? Let's say you're still on compressors, though. You can use what's called hot gas bypass. There are some rules against this in the modern energy code that limit it, but you can still use it in small pieces. So the way hot gas bypass works, if you don't already know, hopefully you're familiar with the refrigeration cycle, and I can skip that. But I got my evaporator, my condenser, my expansion device, and my compressor, my 4 major components on any refrigeration system. Normally, the hot gas leaves the compressor and goes over to the condenser coil where it can reject its heat to the outdoors, right? You're familiar with that. What hot gas bypass does is it bypasses some portion of the refrigerant around that condenser and takes it off the compressor and sends it directly back into the evaporator. And at first you're looking at that going, well, that seems stupid. Why do I want hot gas in the evaporator? Won't that make my evaporator warmer? Yes, it will. Why the hell would you want that? Well, if I have no way of turning my compressor off to get capacity control, I can falsely load the evaporator with the hot gas off my compressor to make it take longer to satisfy the thermostat and get a longer run cycle and hence better dehumidification and all of that. It's not great. And anytime you say the word bypass, it pretty much means energy waste. It's like driving your car with the gas pedal all the way down and the brake pedal halfway down. Like, yeah, you're going the speed you want, but is there a better way to do this? Probably there is. But you can do this to get capacity control. As mentioned, energy code restricts this because obviously it's not energy efficient to run the compressor balls out and then try to throttle it back by falsely loading the evaporator. So energy codes prohibit this, but you are allowed to use it in limited fashion. Specifically, where you're allowed to use it is going to be on the first of many stages of compression. So let's say you don't have recips. You can't do any of that unloader stuff that I was talking about. That wonderful drawing can't be done. You got scroll compressors on a more modern machine, and you can't get the four bare minimum stages. You can only get three because you only need 20 tons of VAV or whatever it is, and it only comes in a three compressorized machine. But you really need more compressor stages. So you can shut off compressor three, you can shut off compressor two, and now compressor one is on by itself, but it's still too much. You're allowed to put hot gas bypass on that lead compressor as long as you're under certain percentage capacity limits of the whole system. You're allowed to utilize that. So it's kind of a way to cheat and get that fourth stage if you can't get it a better way. All right. Another similar thing to hot gas bypass is APR control. Specifically, there's a manufacturer called Rawl that makes these. There may be others that make it. I don't really know, but everybody uses this one. So this is the one that sounds familiar to me, right? Uh, their device does basically the same thing. And when you look at stuff, yeah, the hot gas comes off the compressor. Some of it goes to the condenser coil. Some of it goes through their APR raw device. And if you follow the line, eventually it gets injected right back into the evaporator. Right. So I would argue that it is hot gas bypass. From a code perspective, it counts as hot gas bypass. They just have a slightly better way of doing it. They control it a little bit differently. It's slightly better. Some of this liquid line is coming back into the raw device as well. And somehow through the physics that my brain doesn't understand, it's about 12% less energy waste than hot gas bypass. Make no mistake, a raw device is still energy waste. It's just not as bad as this guy's energy waste. So a lot of you will utilize this. Historically, you've used this as a band-aid. Like someone did everything wrong on the job. It's grossly oversized. You're like, dude, we don't need 80 tons of cooling. We need like 50. Like, what the heck, man? Instead of getting a whole new unit, you might put this on there to get some control over the capacity again. It's usually a retrofit device. You can get them in some cases factory installed as a better version of hot gas bypass, but it's functionally basically the same thing. All right. Sorry, I'm pounding water like crazy. You guys are my fourth class today. I had one in-person class for 3 hours, and then I had two 1 hour broadcasts from the lab. It's like the voice is only going to last so long here. So I'm doing my best to not mess that part up on you. And I got the beer under the desk, but I'm going to wait until 5:45. I'm just kidding. I'm at the office. I don't have any beer. My office is lame. All right. The next thing we could do is we could use a digital scroll compressor. This is a compressor made by Copeland, and it is controlled uniquely compared to other compressors. It is meant to be something similar to what an inverter would do on a compressor, which I'll talk about that in a minute. But it was more readily available before inverters were. Now inverters are more common, obviously, because this thing's been around for like 20 years. So fundamentally, what it does, if you don't know how a scroll compressor works, I probably should get a video of it or something, but we'll see if my pen doesn't do anything weird on me. So if I did something weird, if I was to cut the top of this compressor off and look inside it, there'd be the scroll flange on the top and on the bottom side of it. So there's a scroll like that, and then inside there, maybe I can switch colors. There's another scroll for the bottom piece, and they're intertwined. So what happens in a regular scroll compressor is that one scroll's fixed and one rotates, and as it rotates around, the gap that the refrigerant is pulled into, it gets sucked in and it gets smaller and 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 smaller until it eventually ejects out the top of the compressor through a very small hole. And as it gets smaller and smaller, it's compressoring it, hence the word compressor. It's pressurizing it, and that's how we're getting to higher compressor pressure and hence higher refrigerant pressure and hence higher refrigerant temperature, which I need to send out to the condenser coil. So that's how a normal scroll compressor would work. What happens differently on a digital scroll, I don't know if you can see my face in the little screen here, but if I have the top scroll and the bottom scroll together and they're gyrating, they're doing their thing. What a digital scroll does is it temporarily disengages the two. It like lifts it up. and it's still rotating, but it's not inside the other one, so it's not doing anything. It's not doing any mechanical work. It's not increasing the pressure. It's basically like you paused it and nothing's happening. And then it puts it back together and it does the work again. And then it separates them. Well, what the digital scroll control does is it decides how long to keep them together and how long to keep them apart. If you need full capacity, they're together the whole time. They don't ever separate. If you need half capacity, they're separated half the time. So for example, they might be together for 5 seconds and then apart for 5 seconds, and then together for 5 and apart for 5. And as the needs of the load change, they spend more time together or apart from each other. So that's how it actually controls the capacity. It's actually a really effective way of doing so, and it actually can turn down to lower capacities than we can turn down to with an inverter. So from a pure control standpoint, it is better than an inverter compressor. However, if you ever heard one, it can be an annoying noise. That's the knock on it. That's the negative. You hear that thing, like I'm not good at making noises. It's like going to the auto mechanic and you're trying to describe the car noise. I'm not good at it, right? But it's making that grinding type noise that people don't like. Well, if this is behind some manufacturing facility, who cares? Doesn't matter. But if this is at a school and across the street is somebody's house and they're hearing this thing all the time, yeah, then it gets annoying. So you got to be a little sensitive about where you put it. They're not as loud and annoying as they used to be. Things are better. Sound blankets have helped, etc., etc. But it's not as quiet as an inverter. So that's the knock on it. So it's better control, but it's not quite as quiet. This saves energy compared to hot gas bypass. Hot gas bypass just saves no energy at all, like zero energy savings on hot gas bypass. Now, if you do the raw one, fine, you could save like 12%. So if it's the raw one, maybe you would get a new line on here and it would look like this. Right. Okay. I got the raw one. I saved a little bit of energy. But the digital scroll is a rock star. It has a giant energy reduction. As the load decreases in the space, the power usage goes down because it doesn't consume anywhere near as much amperage when the scrolls are separated versus when they're together. So the more time they're separated, the more energy it in fact saves. So that's an excellent way to do a VAV system if you want to have a compressor on there. You don't necessarily need a digital scroll on every compressor. If you have 4 compressors, the lead one might be a digital scroll, and then the fixed ones could be on off. And if you only need, let's say they're all equally sized for this discussion. So if you only need 25% capacity, you got 1 compressor on, right? If you need less than 25, the digital scroll is engaging, disengaging. If you need, 32%, then you got 1 fixed speed on the whole time, and the digital scroll is engaging, disengaging. If you need 82%, all 3 of the fixed speed ones are on, and the digital scroll is engaging and disengaging, right? So you can do it that way if you wish. You can also put an inverter on the compressor. This is becoming more and more common, and it is for all types of compressors at this point. Obviously, you can get scroll inverters, even residentially. I mean, I've had a scroll inverter at my house since 2015. It's one of the ways. Actually, I don't have that. I have a rotary inverter at my house, rotary compressor with an inverter at my house since 2015, and it's one of the ways to get really good dehumidification. You can get scroll compressors. Ductless mini splits very often have scroll and rotary also with inverters on there. Obviously, large screw chillers can have a VFD on there. A VFD is an inverter, by the way. Screw and centrifugal chillers, or even a screw compressor on and a condensing unit if you have that. You can vary that with an inverter on there. You can't go quite as low as you can with digital scroll. That's okay as long as you stop oversizing crap, right? So start putting things in that aren't oversized, and this will be a lot better story. But you can go down pretty low. 20% is pretty good. The humidity control is fantastic. You can retrofit it, but it's not easy, right? The digital scroll, also same thing, like retrofitting it, you got to be a refrigeration ninja. This is not just something that a controls guy like me is going to go out there and do. That's not happening. You'd have to be pretty good at this kind of stuff. So almost no one retrofits this stuff. Whereas a raw device, they will retrofit on there, right? Or on loaders for a recip, those are easy to retrofit on there. But this stuff would be really hard to do. But it could be done, but it's probably not going to be done. So you're going to buy the machine this way to begin with. All right. That's the ways we can control capacity. So modulating chilled water is good. Lots of stages of fixed speed compressors is good. less stages of fixed speed compressors, but then adding a digital scroll or inverter on the lead compressor. Those would be your three ways in a modern system to get that done. Okay, here's my rules for VAV. I've had these rules since the 90s. Some of them are ones people told me, and I just started doing it that way. Other ones are ones no one told me, and I just started realizing what the hell was going on. There were probably rules in 1960, and they got lost over time. And my job is to reinvigorate those rules to your life. So VAV, by definition, is a cooling only system. It does not heat your building. Stop trying to make the air handler run heat. It F's everything up. If you need heat in the middle of the day for all of your zones, you need a different system. If your building has some portion of it that needs cooling in the wintertime, VAV might be right for you. There is going to be a sensor in the discharge air system, in the supply duct. Its job in life is to provide 55-degree air at all times. There's an exception to that. There's two exceptions to that, which I'll mention. But for right now, 55-degree air all day long. And certainly 55-degree air whenever the building is occupied. All day long, no matter what. It's -3 out. I don't care. Here's your 55-degree air all day long. So that's its job in life. And if zones need heat, great. They can provide their own heaters to do that. Do not expect the air handler to heat during the day. Do not expect the rooftop to heat during the day. With that being said, lots of manufacturers, including Carrier, which is a manufacturer we use at our office a lot, have VAV rooftops that have a dip switch on them that says occupied heating. You're like, oh, I can run heating in the middle of the day. Yeah, it'll turn on the heat in the middle of the day on a VAV rooftop for you. It'll do that. The problem is you don't really want it to do that. Because when you do, every zone gets heat, even the ones in the middle that want cooling. And the amount of airflow you need to keep the rooftop gas-fired heater online is pretty high, probably like 80% of the total airflow of the system, which means it forces all your dampers to go open. So the interior zone that wants cooling all day is now going to take 100% out, 100% heated air in while the other zones get their heat. It's a disaster. Definitely do not try to make that happen. The reason occupied heating is on the dip switches and available to be done is because people asked for it. And factories are not smart and they give it to you, even though you don't really know what you asked for. The only real use for it is construction mode, right? The building's not occupied yet. I haven't even installed the VAV boxes. I don't have any computers. I don't have any servers. I don't have any load. Like, yeah, I might need some heating just to get the building functioning in the middle of the winter, right? Until it gets fully occupied. That's its purpose in life. That rooftop or air handler will, however, as an exception to my earlier statement, run heating in the morning. We call that morning warm up. So the building's unoccupied. It cools off during night. The lights are off. The people aren't there. The computers are off. No one's making coffee. We don't have really any interior load for the most part. So the building gets cool. What we do in the morning is we run the air handler's heater, hot water coil, gas heat, electric heat, whatever we got. We run that heater for morning warm up. Historically, we run that until a sensor in the return air duct warms up to about 68 degrees. And once it gets 68 degrees in the return duct, we say, okay, we're good. Shut it off. Switch over to cooling mode for the rest of the day. Here comes your 55-degree supply air. Let's go, right? That's what normally would happen. More modernly, we don't do it to 68-degree return air. Instead, because we have DDC controls on all these VAV systems now, we look at all the needs of the zones. We basically average all their set points, their occupied heating set points. We average them up and we average all the sensors and we say, okay, once we get up to the average, we're good. So instead of a fixed 68-degree return air, maybe we warm it up until we get to 69.2 degrees space air or whatever it is, because that's what the average is said to do. But fundamentally, it works the same way. If you have large outside air requirements, you probably don't, but if you do, you can use the air handler or rooftops heat to bring the discharge air temperature back up to the 55-degree cooling. You're still providing 55-degree cooling. You're using a gas heater to do it. Because you have such a large amount of outside air that if you just let it come in by itself, the minimum ventilation amount, you'd be at 47 degrees. You need to temper it back up to 55. And you can open up your hot water valve to do that. You could also, on a gas-fired unit, engage the gas heat. However, if you are going to do that, most manufacturers are going to make you buy their modulating or their staged gas heat, and they're going to make you buy the stainless steel heat exchanger because they realize you're introducing a bunch of cold air that's going to cause condensation on the heat exchanger. So they're not going to let you use a steel heat exchanger to do it. It's going to have to be stainless steel. But that could be done if needed, and you'll know that when you design your project in advance, or at least you should know that in advance. It's okay to not provide 55-degree cold air all the time. There are times where you might want to provide 57, and you can get away with that, right? As the season gets to be more mild, i.e., we enter the winter time, maybe I can use 57-degree air, and maybe that's still enough to cool the interior of the building, or 58 or even 60 degrees. I would not go above 60 degrees. You don't want to do this reset in the summertime or even in the collar seasons because I need the colder temperature, the colder dry bulb temperature, in order to also have a colder wet bulb temperature so I can get the coil down to the dew point so I can dehumidify. And 60-degree supplier is probably not going to do it. However, in the wintertime, I can reset the cooling set point upward because I don't really need to hit the dew point because I don't really need to dehumidify in most spaces. I just need to cool the interior. So 60-degree air is enough to cool the building, but not dehumidify it, and that is okay in the winter. So you can do that. Historically, we did that reset with an outside air temperature sensor. And as it got colder outside, we would start resetting the indoor supply air temperature up a little bit higher. In a modern system, once again, we have DDC controls. All the VAV boxes are communicating and talking to the air handler controls. So what we can do is look at all the zones and say, hey, on average, are you guys good? Like you asked me to get, and as a group, you asked me to be 71.8-degree indoor cooling set point. And as a group, you guys are like 70.5. Like you got too much cooling. Why don't we cut it back a little bit here? And I'm going to provide you 58-degree air for a while and let's see how it goes. And you can do that. In fact, the energy codes, which I'll talk about later, require you to do this reset. And they require you to reset it 25% of the way between the supplier and the room temp, and they require the room temp to be no colder than 75, which is probably a shock to most of you. You're not allowed to legally design a commercial or residential building to ever cool below 75 degrees. It's literally against the law. I know you guys don't follow that law, but that's another problem. But 55 to 75 is 20 degrees. 25% of that is 5 degrees. You are required by energy code to allow the supplier temperature reset to float from 55 to 60 when the demand at the zones is not there. If you need heat at your zones, that's not the air handler's problem. That needs to be handled locally. Locally means, like I said before, electric duct heater, hot water coil in the duct, baseboard heater, something of that nature. Do not try to use the air handler to heat the building. It means everybody has to take the hot air and people in the middle bitch. If you don't have an interior core and hence there's nobody in the middle to bitch, you probably shouldn't be doing VAV anyway. Why are you providing cold air the rest of the time when the heat's off, right? If you enable the heat, there's no time. It's either hot or cold. There's nothing in between. So if you don't have a core of the building, you don't need VAV. Do a different zoning system. Long-standing rule in ASHRAE 62, which is the Indoor Air Quality Standard, and the International Mechanical Code, is that you need to have low discharge temperature for overhead heating. This has been there for a long time. I know most people don't follow it or understand it, or maybe they don't care. You can't have really hot air coming out of the diffuser, right? So that diffuser, well, that's a pretty bad, I should have showed you that view. A couple broken ceiling tiles and 2 linear slots. This office I'm sitting in is not my office, by the way. My office is in a totally different city. I just happen to be here. This was my old office back like in 2006. So every once in a while, I still have keys and I come squat here when I need to squat here. But when I had this office previously, there was one diffuser. This was like an old space that we just kind of took over and gutted because I just needed an office. There was one diffuser at the interior wall and the windows all sucked. They've all been replaced and it's better now, although the curtains suck. The sun is bright in here. And I learned a lot just sitting in this particular office about what the hell's happening in some of these buildings. So I did building automation in the 90s, and people would call up and say, hey, dude, it's cold in my building. Like, yeah, okay. What do you want me to do about it? Well, can you fix it? I'm like, I'm the controls guy. Like, what can I'm not, your heat's broke? No, my heat's not broke. It's just not warm enough in here. So I would log in via modem. If you don't know what a modem is, sorry. I would dial into a modem, which is like pre-internet, if you will. And I would change their set point. Like, oh, it used to be 72. Let's make it 73 and see how it goes. And they would call back, dude, I thought you were going to change the set point. Yeah, man, I changed it. It's just, sorry, it's still cold in there. No, it says 73, but it's just not good enough. And I can bump it up to whatever I want. It wouldn't matter. They're still cold. What I learned from a really intelligent VAV guy is that it's not just VAV, it's all systems. When you're heating from overhead, hot air does not want to come down into the space. It wants to stay at the ceiling because it's hot air. That's what it does, right? So sitting in this office with that thermostat over there on the wall, I literally sat here with my little thermal gun. I'm like, why am I so freaking cold? Am I just like a pansy that's not used to working in, not used to, being in cold weather anymore now that I have an office job? And I scanned my thermal gun over by the wall and said the thermostat was 72, right? And I scanned up the ceiling and it got hotter and hotter. And it was like 120 some degrees at the ceiling. It was freaking hot, right? There was hot ass air coming out of the diffuser. Then I scanned down by the floor where my feet were. And it was like 53 degrees. I'm like, it's probably why I'm cold. I'm standing on a 53-degree floor and I'm a wuss. So that's the deal. Why the hell is it so hot at the ceiling? Why is the hot air not coming down? So it turns out what happens is if you want the hot air to come down, you have to do three different things. You have to have a diffuser that throws the hot air to the inside of the room and to the exterior glass. You have to throw it both ways. That's a rule in ASHRAE 62. You have to throw it both directions. You have to pick a diffuser that will throw the air to the glass and 50% of the way down the wall. If you don't throw it at least that far, you pick a crappy diffuser and it doesn't go that far, it's never going to be able to heat this space. And your discharge air temperature cannot be more than 15 degrees above the space temperature. So if you set your space temperature for 75 degrees, your maximum discharge is 90. If you set your space temperature for 70, your maximum discharge is 85. Essentially what happens is if the air is too hot, it just hugs the ceiling longer. And the way you satisfy the thermostat is by heating the wall all the way down slowly over a long period of time. And the floor stays cold and you don't get any mixing of the upper part and the lower part. So you need less heat in order to do that. So when you're picking your hot water coil or you're picking an electric heater for your VAV box, you have to pick it with that in mind. When you do your selection, which you're now doing on software these days, and it may not be you doing it, but someone's doing this, whether it's the engineering firm or the design build contractor or the rep, you have to pick it so it doesn't provide more than 90-degree supply air, or it's going to do a really bad job of heating the space. Somebody just keeps calling me nonstop. I mean, it's all my coworkers, so the same people that left the building already, so that's their own problem. Next rule, got to have modulating cooling. I think I already beat that to death. Chilled water, fantastic. Variable compressors, fantastic. Multiple on-off stage compressors, fantastic. You got to do one of those things because this is all controlled off of a temperature sensor sticking in the supply duct. And any compressor turning on or off, it'll see that temperature change almost immediately in the duct. I have to have variable capacity fans. I already mentioned that to you. We're going to do that with the VFD. That's the only way you're going to do it now. The pressure sensor is going to be mounted in the duct, and then the VFD is going to be controlled to maintain a specific static pressure. The way we've done that, okay, there's three ways. The way you should do it is you should put that pressure sensor at the VAV box that's the furthest one away, and as long as you can get enough pressure there, everybody upstream is going to get enough pressure. The problem is no one wants to run the tubing all the way over there, and I don't even know which one's furthest away. It's not geographically the farthest, it's the one with the biggest pressure drop duct run. I don't know which one it is. And I also got a run going to the left and to the right when it comes down to the building. So I don't know. It becomes hard. So what we've done as a cheat code for the past 40, 50 years is we've run the pneumatic tubing and stuck it in the duct about 2/3 of the way down the duct. I don't know who picked 2/3. That's just what we picked as a rule of thumb. It works pretty good. I like it. No problem. You cannot put it at the discharge of the fan. That's the worst thing. The fan will essentially never ramp down, or it'll ramp between 90 and 100%. Which is crap. You don't want that. You want this thing to be able to ramp down to 20, 30, 40% when needed. So you got to stick it 2/3 down the duct. The code has since changed, and I'll explain what the code requires today, but you're no longer allowed to put it 2/3 down the duct, and you're also no longer allowed to put it at the discharge of the fan. There's a new spot you got to put it, and I will explain that. But for concept, 2/3 down the duct. You need variable exhaust capacity. So as you probably know, as you open up an economizer damper to bring in for your cooling, which is also required in all these buildings, you need to have some kind of way of relieving that pressure. Maybe it's a little dinky rooftop and it's a barometric exhaust. Maybe it's a power exhaust on the rooftop. Maybe it's a two-stage power exhaust. Maybe it's another exhaust fan. Something has to exhaust the air out as you take more air in. The problem with VAV is I have a modulating outside air damper taking more air in for economizer mode, and I have a modulating fan changing speed. So to buy an exhaust fan and have it turn on and off at the right time, no shot at all. So I have to vary the exhaust capacity. That means I got to put a VFD on the exhaust fan also. Or I got to get like 4 little exhaust fans and stage them up in order to have a shot at controlling it. So every VAV air handler is going to have a pressure sensor controlling the supply fan with the pneumatic tube stuck into the duct system. And every VAV system should also have an exhaust system in the building that also has a pneumatic tube, but that pneumatic tube is going to be stuck down in the building, preferably not right next to a door, where every time the door opens, it gets a false reading, or not a false reading, but a correct reading temporarily that's going to go away in a second. So usually mount it over in the hallway. If you have a multi-story building, usually you mount it down on the first or second floor and not all the way up on the 10th floor. Like get it down there. And that sensor is going to be set up typically to maintain approximately, 0.05 inches of static. So some job it might be 0.03, another one 0.08, but something in that general range, which is a fairly low amount, but that's the pressure from inside to outside. So I have a differential pressure sensor. One end of the pneumatic tubing goes outside, the other one goes into a hallway, and I maintain building pressure that way. All right, that was kind of the rules of things you have to have. As mentioned, there's a bunch of energy savings involved in the discussion. There is a diversity credit, smaller equipment. You don't buy the 60 ton, you buy the 42 ton or whatever it was I said, 48 ton I said in my example, right? Because I don't need all the max cooling at all the exact moments. Different areas need max cooling at different moments. I have to have some energy savings coming from all my part load control. Turning compressors off saves energy, right? So all that stuff's in my favor. The VFD, already mentioned, saves a bunch of energy. We can do what's called supply air reset. I already told you about that. That's where we set the discharge air temperature upward when it's not dehumidification season, if you will. And I set it from 55 up to a maximum of 60. You can do that based off of a surrogate outdoor air temperature, or more properly, you would do it based on communicating to the zones and comparing their indoor set point to their indoor actual temperature averages. That used to be an optional thing we did to save energy. It's now a code required thing. You have to do it by code, by energy code. You can also do static pressure reset. So this one's resetting the discharge air temperature from 55 towards 60 as it's more mild outside, and back towards 55 as it gets hotter out, or hotter inside, I should say. Static pressure reset resets the set point of the VFD system. So maybe you got it set for 1.5 inches of static. Okay, great. If I have a DDC communicating system, the main controller of the air handler can communicate and speak to all the zone dampers and say, hey, what position are you guys at? And if nobody's 100% open, everybody's partially closed, well, why the hell am I ramping up this high? Nobody wants all the air I'm giving them. Why don't I just back it down, man? So if it looks at all the zones, and let's just say for argument's sake, everyone's less than 80% open, then the control says, you know what? I'm not giving you 1.5 inches. I'm going to give you 1.4. See how it goes. And then everybody kind of tweaks up instead of being, whatever, let's say they were at 72% was the most open one. All of a sudden it becomes 76% open to try to get more air because you gave me more, or get the same air because you gave me less pressure. And then it's, oh, no one's 80% yet? Fine. I'll give you 1.3 inches of static. Let's see what happens, right? And eventually somebody gets up into that 80, 90% range and we kind of pause it there. And then when somebody gets up above 90, starts approaching 100, we say, okay, well, if that guy wants 100, we probably can't be operating here at 1.1. We got to go back up to 1.2, 1.3, 1.4, and eventually 1.5 when somebody wants max cooling. So that saves you more fan energy by doing that. This is also now a code required thing. So these things all used to be options, VFD, supply air reset, static pressure reset. You got to do them now. It's like bare minimum nowadays. You can also do CO2-based demand control ventilation. This is available on VAV and non-VAV systems, whereas supply air reset and static pressure reset are VAV specific. What that allows you to do is, as less people are in the building, the CO2 sensor doesn't register them breathing. They don't exhale CO2 because there's only 5 people instead of 50. And the less people in the building, the less code required ventilation air I need. So we drop the outside air damper minimum position lower than the code minimum because everybody didn't come to work today. Right? And if they do come to work, we ramp it back up because we recognize it on the CO2 sensor. You can do that. However, when you do that on a VAV system, you also need to involve the VAV dampers. I can't just have the CO2 sensor mounting the outside air damper and the inside nothing's happening, right? So once you do that, every single zone gets a CO2 sensor wired up to the VAV box. And the VAV box can throttle back downward when less people are breathing in there. Now, if it's hot in there for other reasons, it can still modulate more open because of cooling reasons, but it can throttle back below the minimum when less people are breathing. And then what the air handler controller does is it looks at all the zones and says, okay, who's the highest CO2 reading? Oh, it's right there, room number 19. Fine. I'm going to use room number 19 CO2 to drive my damper. And if somebody else ever becomes the highest CO2 reading, I'll use that as my reading. It just looks at it and asks, who's the highest number? I'll control to that one. If I satisfy the one that has the worst CO2, everybody else should be fine, right? All right, questions. By the way, me yelling out questions is just my way to get a drink here. All right. Some of the slides I have here, I'm going to skip because we don't really need to see everything. Like I said, it's, a half day class jammed into hour 45. But there are all types of VAV boxes that you can have in the duct system, right? All of them have one thing in common. They have a piece of sheet metal in there that modulates more open and more closed. And they have a cross flow sampling tube in there that measures the pressure and converts that to a CFM value. Beyond that, there are a lot of differences. Many of these we do not use. They're very special. The ones we use, single duct, that's a regular VAV box. Single duct with reheat, meaning a hot water core electric heat. We use that. We use parallel fan powered and series fan powered. Everything else is special. So those are the four that we typically use. Cooling only with heater, and then two types of fan powered with heater. So those are the ones that I'll spend some time on. A regular cooling only box, this is used for the interior of the building. Probably not super useful on a perimeter unless the perimeter has baseboard heat instead of a duct heater, then that would be fine. But this is used on the interior zones. There's a cross flow on here, as I mentioned. I'll show you some blow up pictures of that to measure the pressure. And we use that pressure along with the dimensional size to calculate the CFM moving through the box. And we can modulate between a minimum and maximum that way. So this is your regular basic VAV box. There are some retrofit kits for weird stuff. No one uses these at all. So they're super, super specialized and generally speaking, long lead time. So we don't use them. They're available. If you want one, someone will get you one, but not normal. We don't do supply tracking very often either. This would be a very specialized space. For example, like a hospital where I'm going to have a VAV box on the supply air and have another VAV box on the return air leaving that space and control them in order to maintain either a positive or negative pressure. So sometimes in a hospital, you might do that or in the laboratory situation. But in general, not common at all. A bypass terminal, I've literally never seen one of these, but it's for a system that is so primitive that it doesn't have a VFD on it. You're just running it and riding the curve, and it's still too much pressure. There's a second damper blade inside this VAV box that dumps air back into the plenum if there's too much. No one has ever bought one. I mean, someone's bought one, but no one I've ever heard of. So we'll skip that one. Dual duct, also super rare. What this does is you have a cooling air handler and a heating air handler, or you have a special air handler that has both a cooling deck and a heating deck at the same time. And you run two ducts throughout the whole building, one with hot air and one with cold air. And then you mix them at the zone to provide them to your diffusers. It provides absolutely excellent, perfect temperature control. You literally mix hot and cold air to get the exact temperature you want. It's phenomenal, right? However, you're taking air and paying to heat it, taking other air, paying to cool it, and then mixing it. It is super inefficient. Plus, you got to run two ducts around the building, which is very costly. So this is very rare that someone would do this. Once again, laboratory type weird stuff like that. But generally speaking, you're not going to see this. Right? So I'm going to skip those discussions for right now as well. Gotta save time somewhere today. All right, fan power boxes. There are two types of fan power boxes that we utilize. There is a series fan powered and there is a parallel fan powered box. Series fan powered provides the same CFM out to diffusers at all points in time. Parallel, the amount of airflow will change, and you'll see why in a second. Reasons why you might want series, why you might want a constant amount of air coming out, is that you no longer have to be as picky with your diffuser selection because you're never going to throttle the amount of air going into that room. Also, from a sound perspective, the sound, the noise is always exactly the same because it's always the same CFM coming into the room. So those would be the reasons to choose series. And then parallel fans there is a scenario in which you get a little bit of free heat, and that's the reason to choose that one. So I'll describe them both, and you can pick which one you want. There's literally no right or wrong answer. There are some engineering firms that prefer one over the other. There's some pockets of the country that prefer one over the other, and literally they have no reason why. They cannot tell you why they do it. They're just like, oh, that's what we always done. That's what Bill, the owner, used to do, and his dad Joe told him to do that. So that's what we always do, and that's the end of the story, right? So series fan power boxes, the way those work, based on my crude drawing here. What you're looking at here is this right here is the primary air inlet. This is the duct connected to the air handler. And then this duct out over here is the one connected out to the branches that go to the diffusers for my zone. And this hole right here is open to the plenum. And the top would not be open. There would be a sheet metal lid on top of that. So there's only three openings: the primary air inlet, the plenum inlet, and then the discharge air. And that fan is in series with the primary inlet. So air gets sucked into here and it goes to the fan. This fan has to run constantly, otherwise no air is going to come out. So that's why it's constant volume fan. So it can suck air in from the plenum when I want heating and only have a minimum opening on this damper to get a little bit of fresh air from the ducted system. And the rest of it can suck it out of the plenum because this dude is 55-degree cold air all the time, no matter what. And the plenum air might be 70, 75, 78 degrees. So I mix some 55 with some 70, and I get a little bit of free heating essentially by using the plenum air. When I'm doing that, I will have it at minimum cooling position. So minimum meaning the lowest amount I'm allowed to have for that zone based on its ventilation needs. When I go to cooling scenario, then that damper opens up and all my air comes through that damper and goes through the fan and down the duct. And nothing comes in the plenum. There's no damper here. I don't need a damper. If I'm providing you 1.5 inches of static here, and this guy's pulling air out of this box, it's going to pull it from the pressurized pathway and not this other open pathway. So when you want full cooling, it all comes through there. Nothing comes through the plenum. But when you have minimum cooling and a little bit of heat to make a mix, that's when you got air coming through both. You always have to make sure that this fan can move more air than the inlet can move. Otherwise, in this example, I'm trying to shove 1200 CFM into the inlet from my main air handler. This fan only moves 1000. The 200 has to go somewhere. It goes back into the plenum. That is not only an energy waste, but it causes the plenum temperature to get lower and lower and lower. Then when someone else wants to get free heat from the plenum, it's not there because I've been dumping 55-degree air in there all day long. So there's no free heat. So the main fan, the series fan, the one in the VAV box here, needs to move more CFM or at least equal CFM to what the primary air can possibly deliver. The difference between standard and premium boxes is just that there's a larger box baffling inside there to reduce noise issues. You can imagine with an opening right here, fan noise can easily discharge backwards out of that opening into the plenum. And depending on where that plenum is, maybe it's right above our return air grate or something stupid like that, it can be noisy. So the premium ones are for sound reasons. Make them quieter. That's the whole reason with the premium one. They cost a lot of money. You seldom will get one. And they're bigger, heavier, take up more space, right? The parallel fan power boxes, in contrast, previously my air handler was connected here and my fan was here in series. Now my fan is over here in parallel. I can pull air through this pathway without the fan being involved. I could not do that on series. Or I could pull air through this pathway with the fan. So on a series fan power box, the fan runs all day long. Whenever this place is occupied, that fan absolutely has to run. It can never shut off. Plus the main air handler fan is running, obviously. For a parallel box, this fan is off all the time. And it only turns on if there's a heat call for that zone. It's the only time it would turn on. So that guy turns on whenever I have a request for heat. So if it's in cooling mode, this guy is off, the fan's off, and all my air is going sailing through the box into the space, just like a normal VAV box, and I pretend I don't own a fan. When there's a call for heat, before it engages electric heat or hot water coil, it'll utilize this fan as its first stage of heat. So that fan turns on, it actually pushes this little barometric damper to block off a portion of this guy, and most of the air now sucks its way through this here. A little bit of air comes around to give me a little bit of ventilation benefit, but primarily I'm heating through this pathway. So this fan cycles on and off with a heat call. If that's not enough heat, so if that's not enough, 76-degree plenum air to heat my space, it will then engage the hot water valve or electric heater, assuming you own one of those. So parallel and series fan power boxes, generally speaking, are used at the perimeter, and then regular VAV boxes are used at the interior zone. And once again, there's you know, the premium, non-premium, which has the extra baffling and insulation material and extra pathways to make sure that the sound is not, make sure the sound's attenuated, essentially. So side by side, here's series on the left, where the primary air is in series with the fan, and here's parallel on the right, where the primary air is side by side with that fan. All right. There are controllers for these fans. Most of these are ECM at this point. You can still find old school ones that are not. But there's some kind of controller on there. Typically, it is adjusted with a little dial on here. You turn that dial to provide more or less airflow. This is typically adjusted by the air balancer on the project, assuming you, in fact, hired an air balancer. VAV systems are significantly more complicated to balance than a traditional constant volume system. You have to adjust the fan, the main air handler fan. You have to adjust the VAV box fans, and you have to adjust the damper, and you have to adjust the diffuser, and get those things all where they need to be in relation to each other. So there's a little bit more work there, but the fans are typically adjusted for speed with a little potentiometer screw on the bottom of the VAV box. I think I skipped it. I don't know if I should have or not. Maybe I didn't skip it. I didn't skip it. Maybe I don't have it. Oh, there it is. All right. Sometimes, so in general, PSC motors are less efficient than ECM motors. You're probably aware since 2019 on furnaces, PSC motors are prohibited. You cannot install a furnace with a PSC motor. Actually, you can install one. They can't manufacture one anymore. So we're 7 years into that. ECM motors are definitely more efficient. However, if you run them at absolute max capacity, an ECM motor is actually less efficient than a PSC. It's just that we don't have a need to run them at max capacity, so this is not a problem. So on this chart, we have watts on the bottom per CFM, and we have flow up the vertical axis. Where my red dot is 100%. If I'm going to run 100% of the airflow of this fan, this PSC motor would use less energy than this ECM motor. But then as I start ramping this thing down, specifically in this case, when I get below, like, I don't know, I'll make up a number, 82% capacity now and below, all of a sudden the ECM motor is using way less energy than the PSC motor can use. And instead of being, over here, PSC motor energy goes up. Energy, not total energy, energy per CFM, watts per CFM. So it's costing me more to get every drop of air, if you will. It gets worse. It goes, in this case, from 0.5 up to 0.7, whereas the ECM goes down. So as long as you're not picking your VAV box, your fan power VAV box, at the absolute maximum range that it can possibly be turned up to, as long as you're picking it somewhere else, it's going to be an efficient choice for you. All right, some things to consider. One, I know I have 2018 code on here. We are on the 2021 code for the state of Illinois. I should have updated that. For the things that are involved in this discussion, it doesn't change. Other stuff changes, but this stuff doesn't change. It's still required. So I should have changed the 18 to 21 and not told you any of that. For certain types of small fractional horsepower motors, they're required to have an ECM. Series fan powered motors for those boxes are required to have an ECM. Parallel fan motors are not required to have an ECM. You can still use one if you want to, but they don't have to, right? So specifically the parallel ones don't because of exception number 1. Motors in the airstream within fan coils and terminal units that only provide heating to the space. They could have just said, if you have a parallel fan-powered VAV box, you don't have to do this, right? But the series fan does, primarily because the series fan operates all the time, literally all day, whereas the parallel fan only operates in the winter and only on a heat call. So it's less operating hours, which is why they don't require you to do it. Liners on VAV boxes, the default standard liner is fiberglass 1/2-inch thick, right? That's there for the purpose of attenuating some of the sound associated with the damper. right? It also helps with condensation, but hopefully you're not having condensation issues that far down the duct. But if you are, it would help with that. It's also the best choice for sound. Literally, the fiberglass insulation is the best choice. You could upgrade and go to 1 inch, and it will be 1 NC. NC is the sound criteria. The lower the number, the better. It'll be about 1 NC lower. In reality, it's not even one. The manufacturers that tested this, specifically the guys at Kruger, I know tested it, they rounded it up to one just to get it to a nice whole number. It's even less than that. So there's probably not really any reason to buy 1 inch thick insulation. Just take the 1/2 inch default. It's good. You can also do other stuff. You can do foil facing on the insulation. You can do double duct, where I have a piece of metal insulation and another piece of metal. The reason to have the foil faced and the dual duct is to make them more cleanable. You can wipe them down. And if you got some kind of specialty laboratory or a certain hospital situation and you need to clean the inside of this duct, those things, in fact, could have a benefit for you. For a regular office building, there's no need to do it. No one's ever going to climb in there and wipe it down. It's never going to happen. So why make it wipeable? It just doesn't, it's not a thing, right? But those things are worse for sound. As you can imagine, fiberglass, which is a bunch of little pieces of glass spun together, when sound goes there, it can get trapped in there and bounce around and get absorbed. Whereas a piece of sheet metal or a piece of foil that acts like a piece of sheet metal will reflect the sound back out. So dual wall air handlers or VAV box insulation is the worst for sound. It's a very large penalty. You can make it perforated, put holes in it, and it won't be as bad, but there's no reason to do that. The whole reason to get double wall is in order to get sound improvement, or excuse me, wipeability on there, cleanability. So putting holes in there doesn't help me. So that's stupid. You shouldn't do that. The foil facing adds another 7 to 10 sound penalty. You don't want that. Doing nothing obviously makes it more cleanable, but it's horrific on the sound. It's as bad as dual wall. You can get cellular liner. Cellular liner is like that closed cell foam insulation. You can get it wet. Water won't even go through it. You can wipe it down as much as you want and wipe it down. And it's not bad from a sound standpoint. It's not great, but it's not bad. So pretty much there's only two real choices, is my opinion. You either get the low cost, cheap, entry level, 1/2 inch thick insulation, which is the best for sound, and roll with it. Or you tell me you need cleanability, you need to wipe this thing down because it's a special laboratory job. Then you should get the cellular foam insulation and have a minor sound penalty. Don't pick anything else. Everything else is stupid. We have all of these. Every manufacturer we deal with offers every one of these things, and you could buy them because some people ask for them. But those are the only two you should even think about. All right, I mentioned earlier there's a cross flow on the inlet of the primary air from the air handler to the VAV box. That is so the VAV box controller can measure, well, specifically it measures velocity, pressure, and static pressure, and it uses that along with you telling it at programming time what the dimensional opening is to calculate how much CFM it is moving. The normal style is a cross flow like this. There is one manufacturer that also has a linear probe on an angle like this. That same manufacturer does offer both of those. They believe that the linear cross flow is less noisy because it doesn't have as evenness to it. It's on an angle and it's not the other angle. It's only one angle, so it breaks up the sound wave. That's their what they go with. But they also offer the cross flow because that's what all their competitors have. So they got to be able to do that. So those pressure probes measure both velocity pressure and static pressure. Velocity pressure, if this is my probe, my fingertip is the opening. Velocity pressure moves into the tip. So how much pressure is being caused by the air moving itself. Whereas static pressure is how much pressure is pushing on the outside walls of the duct. These probes measure both of those things simultaneously. So as air is coming into the duct system, I don't know if you can see the damper back there. This is before we get to the damper. Air is flowing this direction, and there are holes in the probe that measure the velocity pressure. And then on the back side of the probe, that's my velocity pressure measurement. And on the back side of the probe, there's a couple other holes that measure the static pressure. So air in this case is coming this direction, and these holes don't see that. They don't see the velocity coming into the hole because they're on the other side of it. So that's the static pressure measurement, and this is the velocity pressure measurement. And both of those are used to calculate it. In the interest of time, I'm going to skip all the math and discussion on how that all works. Just believe me that you need to measure both in order to calculate the CFM, right? There's just different size VAV boxes for different needs on there. Most common sizes tend to be like 6, 8, 10 inches. You can get a 4 or 5 inch. It's kind of a waste of money because for most manufacturers, they just ship you a 6 inch with a reducing collar on the inlet of it. Well, hell, I could just bought a 6 inch and put my own reducing collar on there, probably cheaper. You can also get a 7 inch. People don't typically like to use odd sizes. So 7 and 9 are pretty rare. Most people just use an 8 or a 10 and call it a day. But there are different sizes for different amounts of airflow that you need going to that particular zone. Hot water coils are available for all these VAV boxes as well. You can typically get 1, 2, sometimes even more rows of coil on there, and you're picking the amount of heat that you need in order to approximately to get the BTUs that you want at a flow rate that is appropriate to keep yourself under a 9-degree discharge as well. When you're ordering these, not only do you have to tell them how much heat you need, but you have to tell them if you want left or right hand connections. And sadly, you tell on the VAV box if you want left or right hand connections, meaning what side I want my actuator to be on. And that does not have to be the same side the water is on. Usually it should be the same side. If you have space on the left side to make your piping connections and install a valve, you probably have space on your side for a control enclosure and an actuator. But you don't always have that. So you can pick them opposite, which is weird, but it can in fact be done. You can also do electric heat. With an electric heater, you have several different options. You could pick the voltage that you have, right? Usually it's going to be 3-phase because there's a lot of heat involved in all these boxes when you start adding them up. So you're picking 208 or 480. You can do single phase. That is rare, but you can ask for that. Or maybe you got one little tiny small zone. It doesn't really need a big heater. You can get, 120 volt single phase or whatever there. You can do that if you want to. So all of those voltages are available, every possible scenario. The one thing that is not available is 408 3-phase 3-wire. That is weird. It's not something that exists in most places, but there are pockets in older Chicago areas that have that. You need to special order that from your VAV manufacturer. And you probably should do it special order for all of your equipment on the job. If you have a job that has 3-phase 3-wire instead of 3-phase 4-wire. Three-phase 4-wire means I have line 1, line 2, line 3, and a neutral, right? 3-phase 3-wire is a hot mess. So there are places that have that. Medina Temple, downtown Chicago has that. There's weird little pockets that have stuff like that. So just pay attention to that. So you have these electric heaters that you can use. You can get typically 1 or 2 stages of heat. Sometimes you can also get a 3rd stage of heat. If you need more precise control, there are a couple options for modulating electric heat. These are newer, meaning they become available in the past 15, 20 years, but you can in fact do this. So you can have an SCR control. That's the normal way to do it. Think of it as like a potentiometer for heat, like a dimmer switch on your lights. You can have that resistance value added in there to reduce the amount of flow to the heater. But it's obviously automated. You're not doing it with an actual handheld dimmer switch. So that's an SCR control. You can also do solid state relay, where essentially it pulses the heater on and off. For purpose of quick explanation, it's like that digital scroll compressor. Oh, 5 seconds on, 5 seconds off. Oh, you need more capacity? 8 seconds on, 2 seconds off. It's exactly like that, but for electric heater. You need a lot of capacity, we just run it all. You need half capacity, I'm going to run it for 5 seconds, then I'm going to turn it off for 5, then on for 5, then off for 5. It'll pulse it on and off. So you can do that. Pretty much every manufacturer has one or the other of these, or they have both in some cases. So those are all the different choices on how you can control that electric heater. All your major VAV control manufacturers can control this heater one way or the other. Some of them have to trick it, and they have to tell their controller that it's a hot water valve. And most of their hot water valves have 3-point floating outputs, and you can order the heater that way if you have to. So the VAV box thinks that it has a hot water heater, but it really has a pulsing electric heater, but it works fine. Control-wise, you can add your controls to the VAV box in the field with your favorite controls manufacturer, or you can have them factory mounted for you. If it's a really big job and you have plenty of lead time, it probably saves some labor effort to have them factory mounted. But what you do is you send all your drawings in to your supplier. They put it on their paper and redraw it. They send it back to you for you to verify it. Probably messed it up, send it back again, they send it back and verify it. You finally agree that the drawing's correct on their paper, and then you ship them all of your controllers. Once they receive every single thing you're supposed to ship them, then they begin building your VAV box. So like I said, a long lead time project where you can afford a few weeks of jerking around, great. You want to mount the controllers for me on my 275 VAV boxes, it'll save me some field labor. And generally speaking, Chicago field labor for an electrician is probably more expensive than wherever the Texas facilities that this is made. You only got 10, 20, 30 VAV boxes and you need them like in 3 weeks. You probably shouldn't mess around with that. Order the VAV boxes, mount your own stuff. You can do DDC controls, you can do analog controls, and you can do pneumatic controls. I would say at this point, 95% of what everyone would do would be DDC controls. The only reason you'd ever order pneumatic or analog is you're adding or replacing one VAV box on an existing system, and it needs to work with obviously the existing system. So you're buying it old school to make it work kind of thing. As mentioned, you can get left or right-hand connections on everything. The electric heater section, the hot water coil stub outs, and the controller box. A few other things that are required by code for you. Anytime you're going to be utilizing, anytime you're going to reduce the airflow for the purposes of controlling capacity of the system, you're going to have to put a VFD on there by code. Specifically on chilled water, if your fan is more than 1/4 horsepower, so it probably is, and on DX, if your cooling capacity is above 5 tons. So pretty much everything. So if it's VAV, just plan on there being a VFD on there. It's going to have to happen, right? Automatically, that's happening. You also need capacity control. I told you before it's a really good idea. Now I'm going to tell you it's actually a flat out requirement. As soon as you decide to modulate airflow to maintain temperature in a zone, as soon as you do that, some rules kick in. So first off, on every system, unrelated to VFDs, as soon as you have 75,000 BTUs or more, 6.25 tons and larger, you are required to have a minimum of 2 stages of compression. A single stage 10-ton machine is not allowed anywhere in the state, and it hasn't been for a while. Stop installing them. That's stupid. In fact, at this point, you should be doing 2-stage equipment on everything, even at your house. Like, what are you doing? Let's figure this out. If you decide that you are going to have systems that control space temperature by modulating airflow, i.e. a damper opening and closing to let more or less cold air in, then you need to either go to 3 or 4 stages of compression. If you are between 5 tons and 20 tons, you need 3 stages minimum. And if you are above 20 tons, you have to have at least 4 stages on there. You could also go the route of doing variable capacity. So you could have one compressor that gives you the variable capacity equivalent of 4 stages by being able to ramp down to 25%. You could do that too, right? But a lot of times on these mid-size condensing units for VAV, you're going to get a bunch of little scroll compressors. As mentioned earlier, there's a hot gas bypass limitation for the code. So specifically, you can use hot gas bypass. You cannot use it as one of these stages. It legally does not count as a stage. It kind of acts like one, but it doesn't count. You're not displacing the compression. You're still running the compression capacity. And then you can also only do it basically on the lead compressor, and you can only do it up on small systems up to a maximum of 25%, and on bigger systems, a maximum of 50% of the compression could possibly have hot gas bypass on it. You'd like to avoid this if you can, but sometimes it's hard. I mentioned to you previously that there was a code rule change on where the static pressure probe gets located. Historically, it gets mounted 2/3 down the duct. We guesstimate that, we pop it in, we call it a day, no one cares. Now, per the energy code, statewide, you have to install the probe in the duct wherever it will result in exactly a 1.2-inch static pressure set point of your main air handler fan. So you're going to guess, and you're going to measure it, and then you're going to guess again and measure it, and then guess again with your manometer, and then, all right, this is the spot. Great. I can maintain everything at 1.2 inches static if I measure it right there. And then you got to poke the probe in there. In practice, it ends up being about 2/3 down the duct. As mentioned, the static pressure system needs to be reset based on the zone needs. If you still have a pneumatic or analog system, you do not have to do this. The code only requires you to do this particular item if you have DDC controls. You probably do. This is where we look at all the zones. We communicate to them and say, hey, nobody's all the way open. What the heck, man? Instead of 1.2, I'm going to provide you 1.1. Let's see what happens. That's that whole sequence. And as mentioned, you're required to do supplier temperature reset. That is part of the code as well. You have to reset it, as I mentioned, at least 25% of the way from the duct temperature to the indoor temp. So basically that means about 5 degrees. So you got to reset it from 55 up to 60 if the zones want that. You don't have to look at the zones to do it. On DDC, you'll look at the zones to do it. But if you don't have DDC, you could buy a separate controller or buy a separate outside air sensor, excuse me, and do it off of that. And as mentioned, small motors like series fan power boxes have to have ECM motors. Additionally, as you probably know from an energy code standpoint, you are not allowed to simultaneously heat and cool air. That is against all of the rules. You cannot do that. So that needs to be avoided. However, there's an exception for VAV. You are allowed to have air running through the cooling system. And by the way, free cooling economizer air counts as cooled air. You cannot take free cooling economizer air and mix that with hot air either, right? So there's an exception for VAV, and basically the way the exception works, it's all written on the screen here, but it's pretty wordy. Essentially what has to happen is before you energize your local zone heater, before you turn electric heater on or open your hot water valve in that particular zone, you have to first modulate the zone damper back. You can't just leave it wide open and then turn the heater on. You have to first try to solve the problem by modulating the damper more and more and more closed, right? So you modulate it more and more and more closed, then you can energize the heater. And if the heater needs more CFM to stay online, you can start modulating it more and more open. For the most part, you don't have to think about this because every DDC manufacturer already knows this. It's been in the rules for a while. So they already do it this way. If you had an old system, then you're under the old code, so who cares? So new systems, it pretty much is happening on its own. All right. Home stretch. None of you have typed a question in. Not one person's typed a question in. So I'm actually slightly offended. I need you to ask questions so my voice can have, 30 seconds of reset. But no one did that. But if you get a question, type it in. So real quick, the last few slides here are describing the controls that you would be putting on an air handler. I'm gonna do it from a generic standpoint. I'm not picking a particular brand. Just ignore the giant carrier logo in the corner. But then again, these slides are literally from 1998, so it's not like it's a specific controller we make anymore anyway. This is how we typically draw a pictorial of an air handler. I have outside air coming in on the left. I have return air coming up on the top right. That return air either mixes with the outside air and becomes the supply air, or it can exhaust out for pressurization control reasons. It's a normal air handler schematic, right? So first thing I have to do is I have to control the fan. I have to turn it on and off. Got to do that on every air handler. It doesn't matter if it's constant volume or if it's VAV. Got to do that. So I'm going to have a relay that turns the fan on, and I'm probably going to want to prove the fan is on. So there's a lot of ways to do that with a pressure switch, with a sales switch. I personally like to use a current sensing donut where it measures the amp draw increasing through the fan. And if you didn't know, if the belt breaks on a fan, the fan will actually draw less amperage, not more. So you can use this as a way to prove the fan's actually running. And then once the fan is actually running, I use that as my start signal to start doing the math that's required in all my heating and cooling routines. We got the economizer control, which on an air handler, we don't call it an economizer. We call it the mixed air dampers, but it's functionally the same thing. It is typically 3 dampers, one on the outside duct, one on the exhaust duct, and one in the return duct path. And those things work together as a team. The outside air damper, the more that it opens, the more the exhaust air opens, because the more outside air I suck into the building, the more the building gets pressurized, and hence the more has to be exhausted out. The return air damper operates opposite of those two. So the more outside air I bring in, the less air I bring in this pathway. So for example, if I'm bringing 100% outside air in, this guy is 100% open, this guy is fully closed, and no air comes this way. That's okay, because if he's 100% open, so is he, and all the air goes out the top pathway. So the exhaust air and outside air modulate the same direction. The return air modulates the opposite way. You can have each one of these wired to your DDC controller, or you can be cheap and you can wire all of them to one output on the DDC controller and reverse the action switch on this particular one. I'm saying being cheap, but like sometimes you got a controller that only has 8 outputs and you need 9. I don't want to buy another controller. So yeah, I'm being cheap by forcing that one to copy his brothers. From a mixed air damper standpoint, we also need a mixed air temperature sensor. When it ships to you, it's all coiled up like this. Inside this copper tube, every X amount of inches, there's a little thermistor sensor, and they all get electrically averaged together into one value that reports back to my controller, and you serpentine it throughout the coil. See if I can draw that. Ooh, where'd my mouse go? What the beans? There's my mouse. Okay. So let's say I'm looking into the airstream. So I'm standing right here in this outside air duct, and I'm looking down that airstream right that way, right? And this is my cooling coil I see. I mount the mixed air sensor here, and then I serpentine it up and down the. Oh, I hate that thing. Why is it doing that? It's like it's trying to like sync it to something. In any case, I serpentine the sensor up and down so it gets an average. Because what I don't want to happen is I don't want 0 degree air to come in here on a cold day and 7 degree return air to come in here. And the bottom of this thing is seeing 0 and the top is seeing 70. And if I only had one sensor, it'd be wrong. It'd be in one spot or the other. So by averaging it, I get a better representation. The other thing I could probably do is I could put an air blender in, right? Which costs a lot of money, but I could do that, get an air blender in and put the sensor further down. But this is the easy, normal way that we would do this. This sensor looks a lot like a freestat sensor. It is not a freestat sensor. A freestat sensor is a separate device, right? This one is actually just measuring the mixed air by averaging it. A freestat would look really similar, but instead of averaging these sensor probes in here, it would just take whatever one's the highest, or excuse me, whatever one's the lowest, and assume that's the old crap point. So if right down here in the bottom of the coil, it's 36 degrees, but up here it's 50. 36 is what I care about, right? So it looks similar, but it works differently. I'm going to add outdoor air temperature sensors on here in order to control the economizer free cooling mode of this thing. I'm doing this on all air handlers, not just VAV, but I'm adding to this VAV one. And if I'm more savvy, I'm going to add outside air temperature and outside air humidity. And if I'm even more savvy, I'll have return air and return air humidity and do differential enthalpy calculations. But basically what ends up happening is if the space wants cooling, which on VAV, it always wants cooling, if I have outdoor air conditions that are good enough to free cool, I'm going to open the damper and not open the chilled water valve or turn on the compressor. Just not do it. Let it all come in from outside. So that's what those sensors, excuse me, are for in this case. I also got chilled water and hot water coils in here. I could also instead have a gas burner, or I could have an evaporator coil connected up to a compressor for DX, system. But right now it's a chilled water valve in my particular example. That chilled water valve must be modulated for VAV. It cannot open close. It has to modulate. And specifically, it modulates based on a temperature in the supply duct. That temperature sensor is always set for 55 degrees. There are some very rare exceptions to that. I had one job we did where it was 48 degrees. It was a cluster F. 55 is the number. Just trust me on that. Do not design anything different. So 55 degree supply air, and we just constantly keep moving the modulation of that valve to maintain 55 degree air. If I have compressors, I'm turning them on and off to maintain 55. And the less compressors I have, the much harder it's going to be to do that. There may or may not be a space temperature in this system. Typically, there is not. There's a space temperature on every VAV box, but there very rarely nowadays is one on the air handler. But historically, we had a space temperature on the air handler, and that was for nighttime setback mode. At nighttime, we basically just opened up all the dampers. We ignored the existence of them having controls. And if it got cold in the space, like below 60 degrees, we would energize the heat. Or if it got hot above 80, we'd energize the cooling in the middle of the night, just to kind of temper the building or whatever, right? And then we'd ignore that sensor during the daytime and run 55 degree cooling. But nowadays, we don't typically do that. We just use the DDC system to look and see what the zones happen to be doing. We're going to have a hot water coil as well, right? Or it could be a gas heater or electric heater or something else. But in my case, it's a hot water coil. I'm going to modulate that based on the same exact supplier temperature sensor I had. I'm only going to modulate it during morning warm-up. After morning warm-up, you don't get heat. I don't care about you anymore. I'm running cooling only. So it modulates during morning warm-up to maintain a specific discharge air temperature, typically like 90 degrees. And I use that to warm the space up initially in the morning. And once we're warmed up, it immediately shuts the hot water valve and then immediately starts opening the chilled water valve. There's no dead time in between. Just boom, boom, done. I'm going to, unlike a constant volume air handler, I'm also going to have a pressure sensor in the duct, like I mentioned. Maybe it's 2/3 down the duct, maybe it's the new code location, and that pressure sensor is going to be utilized to ramp the VFD up and down, as I already mentioned to you. This drawing is old from the 90s, and there's also a high pressure switch on here. That is not needed. It probably wasn't needed in the 90s either, but it was a carryover from old stuff. The concern back in the day was that VFDs were not reliable because they weren't, and the guide vanes often broke with the dampers, the little guides in different spots. So the control of capacity for airflow sucked. So what they did is they put a high pressure switch in there, and if for any reason the VFD just ramped all the way up and it didn't, its control broke and it was a piece of crap and whatever, we just kill power to everything and shut it all down. That's no longer needed. VFDs are much more reliable now. I have never seen a VFD since I started in 1997 ever like just run away and keep running and never turn off. So not a big issue anymore. I never used one. I started doing controls in 97. I never put a high pressure switch on the VFD. My original boss wanted us to do it. And I was like, why? What is it going to do? I already got this other pressure sensor. Why do I need two pressure sensors? Well, this one's hardwired in case all the controls take a dump. Like, you mean the controls that we're programming? They're not going to take a dump. We're programming them. We're smarter than an average idiot. We weren't, but in this case, we were. You can have a dirty filter switch across the filter. That's a pretty normal thing to have on an air handler. A free stat, as I mentioned, it's a coiled up copper thing. When it ships to you, you once again serpentine it up and down the coil, and it will kill power to the fan, and it'll also report back to my controller if it should happen to trip. So the mixed air is an averaging sensor. The free stat, any one individual segment of it could cause it to trip. If the free sensor goes off, the sequence of operation is as follows. The reason for the free stat is to protect the hot water coil. If you don't have water, you have a gas-fired heater and a DX compression unit, you don't need a free stat. This is for only if one of your two things are a water coil. So if the free stat limit gets tripped, typically it's set for 37, 38, 39 degrees. And for an air handler that's supposed to provide 55-degree air, if you get down to 38, that's bad. So if the free stat trips and says, oh, it's too cold, man, we shut the outside air damper to stop sucking cold air in, because that's probably what's tripping the free stat. We shut the exhaust air damper, primarily because it's interlocked to the exhaust fan. But if I'm not sucking air in, I don't need to suck air out. We open up this damper, right? We do that so that way any heat that's coming up the return kind of drifts its way through. We disable this fan and this fan so it doesn't continue to suck air in through our cracked, leaky, crappy damper, right? So damper shut off, fan shut off. The hot water valve obviously opens. I have a freeze problem. Give me hot water. That opens up. And then, believe it or not, the chilled water valve is also required to open. And that one confuses people. And a lot of people program that backwards. We want the chilled water valve to open as well, because if it's closed, that means this water in the coil is stuck here with air touching it that's very close to freezing. That's not good. So we want to open up this valve, which means cold 44-degree water from the chiller is going to flow through here, but 44-degree water doesn't freeze, right? So I want the 44-degree to start flowing through this thing because that's not going to freeze. The chilled water is literally warmer than the cold air at this point, so I'm going to take it, right? Plus, moving water is kind of tough to freeze anyway. I'm constantly getting new water and sending it back into the building to accidentally warm it up. Smoke detectors can also be part of this discussion. They're required by code. They have the exact same sequence of operation as the free stat, which means shut the outside damper, shut the exhaust damper, open the return damper, turn off the supply fan so we don't circulate smoke into the building, turn off the return fan so we don't circulate smoke in the building, and then just go ahead and open up the hot water and chill water valve just to be safe. Questions? I went 6 minutes over. I talked as fast as I could, people. Anybody have any pending questions that I can answer or not answer? I'll stick on for a minute or two to see what you guys got. It's seeming like we don't have any questions. If you do think of something later, and it's, a VAV question or something random in general you want to ask me, feel free to send me an email. My email's at the bottom down there. I teach classes all day, but eventually I'll get caught up to you. So don't send me your emergency needs that way. But if you have some random thing you want to learn about, my job is full-time training. So that's what I do. So I'm happy to answer your questions. With that, Thank you guys for your time, and I'll see you at the next thing that we do.